and then I'm going to tell you why you actually shouldn't be doing it that way, and how it would be, how is the better way of doing it. So just the problem statement, right? We have the web page, and we have a Poisson distribution with a mean of 30, and we have an 8-hour measurement, and sorry, we have 8 1-hour measurements, and we get a sample mean of 32 orders per hour. So let's first of all establish what is our null hypothesis. Well, it is that the new web design did not create any changes, so we're saying H0 is lambda, which equals 30. And we therefore want to check, can we reject that null hypothesis at the significance level that we would be expecting here. And now we know that the expectation of x is 30, and our variance of x, for a Poisson distribution, we know variance equals lambda. So that means we have a variance of 30 divided by the number of measurements, which is 8. And so because for standard deviation, we had standard deviation of the individual measurement divided by square root of n. So obviously for the variance, it's variance of the individual measurement divided by n. And so we get a standard error of x hat, which is now the square root of 30 over 8, which is 1.936. And if we're now doing the approximation of a normal distribution, right, then our test statistic z is x hat minus 30, and so the estimate sample mean minus the expectation divided by the SE. And so this is 1.937, and that is 1.033. Now, we are doing a one-sided significance test, and because we're only interested in has the web traffic increased. If it actually led to a decrease, then that's not something that we want. And so for alpha equals 0.05, the one-sided critical value is 1.645. That's you get from the tabulations. Right? That's just follows from the phi values. And you can also say that the critical mean, and so the threshold basically where we're saying if the mean is beyond that particular critical value would be 30 plus 1.645 times 1.9365, which is 33.18. And so for that reason, another way of phrasing it is to say, well, the p-value that we are getting is 1 minus phi of our test statistics at 1.033, and that is 0.151. And so no matter how you phrase it, right, our p-value is larger than the significance level alpha, or we can say that our estimate, our sample mean that we're getting to 32 is less than the critical mean of 33.18. So in all cases, we fail to reject the null hypothesis. And so repeating from last time, keep in mind that this is the only statement that we make. Right? We cannot say with the required significance level that the website improved things. However, we also cannot say that it failed to improve things. Right? We just have an indeterminate statement of, well, we don't really know what happened. There's not sufficient statistical information to make this determination. Now, the other thing is that if we're now going to a 1% significance level, and then we actually say that our critical value, so this was A, B, the critical value, our Z.99 is 2.326. Our critical mean is 34.5, right? It's 30 plus 2.326 times the variance here. So, of course, we are again fail to reject the null hypothesis. We wouldn't even have to make any particular computations here, right? Because if we can't even reject the null hypothesis at a 5% significance level, then obviously we have no chance of rejecting it at the 1% significance level. So this was basically running through the cookbook recipe. Now, who can tell me what is the weak point in this whole argument? Exactly. We are assuming, with all of our values here, critical value and so on, that we have Gaussian statistics. But right in the problem statement, we're saying we have Poisson. And this is, again, something that you will find quite frequently, that people are working with all sorts of statistics, and then for the significance test here, just using the Gaussian approximation. But this is, of course, strictly speaking, not valid. So what you actually should be doing is to say, well, you should compute the tail probability for a Poisson distribution, and then saying what is the probability that happens. And then so for the, we could say here that, well, for the total 8-hour interval, we're basically saying, well, we have a Poisson distribution of 240, and from that we can just say, well, what is our probability that the t is larger than 256, given that our lambda is 240. You can compute that, and that is 0.158. If you compare that to the p-value that we computed here of 0.151, it's actually not such a huge difference. The comparison, the conclusion that we cannot reject the null hypothesis would be the same in both cases, but of course that's luck here and coincidence. In terms of, well, if somehow our threshold had been at 0.155, and then with our alpha, then we would have come to opposite conclusions in both cases. So you've got to be very careful when you have knowledge about the statistics of something. Then you really should be computing your critical values based on those statistics, not on the Gaussian statistics. Okay. I also wanted to briefly recap what we were talking last time about the radar. I think there was a little bit of a uncertainty about the different types of errors and how they are being impacted by the choice of the threshold. So let me again draw that picture of the receive voltage and that we are getting under the two different hypotheses. And we were saying that we have, under hypothesis 0, we have x equals n, and this is just if we have noise only. I'm going to draw this now with a much larger noise variance to make the example clear, so this should be symmetric around 0. And the other case is that we have a v plus n. And I'm going to draw this now with a sort of overlap here. And so this is v, this is the mean, and we have a Gaussian variation around it. And this sigma here and this sigma are the same, even though it doesn't look that way because I am bad at drawing, but it's of course the same amount of noise that we have in these two cases. And so, side note for anybody who knows radar. This is, of course, not how a radar detector actually works or should be modeled, because typically we would be going with the received power. We would have some rectifier somewhere, and or we might have a coherent receiver, in which case we would actually have a complex signal, and we might be dealing with the amplitude of the complex signal. Therefore, the noise that we have superposed in there has different characteristics, and so on and so forth. And so this is an oversimplification for the purpose of explaining the concepts. This is not an actual radar. That being said, we were saying that our basic hypothesis test, and therefore the decision of whether we are saying airplane or no airplane, is based on a threshold. And the threshold need not be here somewhere in the middle, right? It can be at some arbitrary level gamma. Now, let's think again of what is the probability of the different types of errors. Right? I'm saying that if my received signal is above this threshold, I'm deciding that there is an error. So the false alarm probability, the probability of deciding there is an airplane, even though there is not, is just the area under this tail here. Right? Because by definition, we're saying it's the probability of deciding for hypothesis 1, meaning the airplane is here, even though hypothesis 0 is actually true. Right? And that happens exactly when I have so much noise that my decision variable is driven into the area A1, into the set A1, right, with which we have associated hypothesis 1. Right? So this is my false alarm probability. My misdetection probability is the converse of saying that, well, it's if this is true, but the noise with a negative amplitude is driving my overall received amplitude below that threshold. And so I'm going to mark it like this. It's this tail area here. And as I'm now moving the threshold around, it's very clear that I'm changing my false alarm and my misdetection probability. And if I move it to the right, well, this area that I filled out solid becomes larger, and that area here, meaning the false alarm probability, becomes smaller, and vice versa. And that gives me that trade-off between the misdetection and the false alarm probability. So how can I get 100% false alarm probability? Well, just by putting my threshold somewhere out here on the very right. And this is, of course, a stupid design. And if I say, even when I have a noise-free case and the target is there, I'm still deciding that there is no target, and then obviously that is not a physically meaningful design, but that is the way in which I can minimize the false alarm probability. Right? I just never say that there is a target hit, and vice versa again. And so this is the thing that lets me move on the curve, where it's a P false alarm and P missed detection, and I'm always going to work here on this sort of curve. And as we know, this is the so-called ROC curve. Sometimes you, instead of misdetection, you're doing the 1 minus misdetection and 1 minus false alarm. So often you see the curves being shaped in this, but that's just a representation thing. And then the other question, so changing gamma basically means you're moving up and down on this curve here. And then changing your SNR means you're getting different curves. And because if I'm taking now a different signal to noise ratio, let's say the noise level has stayed the same, but my signal has increased, and then I have a very different curve. I can probably move my threshold somewhere here in the middle, and I'm going to have a very small both misdetection and false alarm probability. So I'm going to be somewhere here, and then I would have to, again, do something not very smart, moving my threshold over here or over here to really see some very significant values of misdetection and false alarm. And depending on what your SNR is, right, you have this curve, or you have this curve, or you have this curve, but that is sort of a parameter of your measurement. The decision that you're making as a signal processing designer is where do you put your threshold. That's where this comes into play, that trade-off between false alarm and misdetection probability. And then when you're doing an optimization, and again, as I mentioned last time, you have two possibilities. You can say you have a weight plus, times the probability of misdetection plus another weight times the probability of false alarm with a side constraint of W1 plus W2 equal 1. And you want to minimize this weighted error or bad behavior of the radar, or you can say you want, minimize over, let's say, your threshold gamma. And the other possibility is to say that you want to minimize over your threshold gamma the probability of false alarm such that probability of missed detection stays below a particular threshold. Let's call that, I don't know, psi. Right. These are the two typical forms of a system optimization that's connected with a hypothesis test. Which one it is really a choice of the designer. The mathematical tools that you need to tackle that might actually be different. And in one case, it's typically just a straightforward minimization for a single parameter. Here, you're probably going to use some Lagrangian to take the inequality constraint into account. But that's beyond what we're doing here. But you need that connection between the false alarm and the misdetection probability for this. Any more questions on this topic? Okay, if not, let's move on to some additional tests that we want to deal with. So when we're doing now the optimization, or we're doing the decision between the two hypotheses, we can again make some slightly different or design different tests. The first one is the maximum a posteriori test. And in this one, we say that a outcome S is an element of the set A0, meaning we're deciding for hypothesis H0, if the probability of H0 conditioned on the outcome S is larger or equal to the probability of H1 conditioned on the outcome S, and it's S is element of A1 otherwise. And very similarly, if we have an experiment that creates a random vector X, then we have X element of A0 if probability of X conditioned on H0 divided by the probability of X conditioned on H1 is larger or equal to the probability of H1 divided by the probability of H0. Now, in this thing here, we have made two important changes. Right? The first one is we went from a scalar outcome to a vector outcome. That's just a notation change. But the more important thing is that here we had H conditioned on S, right? And here we now have S conditioned or X conditioned on H. And so we flipped things around. And of course, this is the quantity that we can find out from our probability model. Right? Whereas the other thing, but this is the quantity that we really want to find out. And so if you're thinking back what we discussed maybe about a month ago, the difference between a maximum a posteriori test or decision and a maximum likelihood decision is we are taking here into account the prior. And so the reformulation, of course, is just an application of Bayes' theorem. But when we see the end effect here, we're basically just saying that, well, we have prior knowledge of the probability of hypothesis 1 and probability of hypothesis 0. And we're bringing that prior knowledge into play. Now, in a bunch of situations, we pick our partitions of our set. In other words, the likelihood for H0 and H1 to be identical. So we pick our partitions such that the probability of H1, prior probability of H1 and of H0 is identical, in which case there is no difference between maximum likelihood and maximum a posteriori. However, there can be significant differences also, and the radar example is a typical case. Right? If I actually find that doing correct or that lowering the misdetection probability is more important, then I will pick my threshold accordingly, and my prior probability for hypothesis 0 or hypothesis 1 is going to change significantly. And so that should be incorporated in your computations. We secondly can have a minimum cost test. So we're saying C10 is the cost of a false alarm, and the C01 is the cost of a misdetection. Then you're just saying, well, the expected value of our cost is, of course, the probability that we have A1 conditional H0 times the probability that we have hypothesis H0 multiplied with the cost of that particular wrong decision, and plus P of A0, meaning we decide for H0 even though H1 is true, times the probability that H1 actually happened, times the cost of that misdetection. And then so the decision rule actually becomes then very easy again. We decide for X element, X is coming from the set A0 if the probability of X conditioned on H0 divided by probability of X conditioned on H1 is larger or equal probability of H1 times C10 divided by probability of H0 times C01 divided by C10. And so it's basically the same equation, just that we're weighing these probabilities, these priors, with the cost that occurs in a particular context. Right? And so what would be a typical example? Well, let's say you have a sensor on an airplane that warns you whether the wing is going to fall off. And so if you have a false alarm, then you have to send out the technician. The airplane is going to be on the ground maybe another hour or two, and that is associated with the cost. If you have a misdetection, then and the airplane starts anyway and then falls from the sky, then that cost is somewhat higher. And you would incorporate that in your hypothesis test. Now, another important type of test is, of course, the maximum likelihood test, which says we do not know the a priori probabilities, and therefore we simply decide that X is element of A0 if the probability of X conditioned on H0 divided by the probability of X conditioned on H1 is larger or equal than 1. And that's why I was saying that, well, if the priors have equal magnitude, then of course maximum likelihood and maximum a posteriori become the same, because then even the maximum a posteriori, the right side of this equation here, becomes 1. And then finally, we have the Neyman-Pearson test. And that is now more related to the question of, okay, we have a constraint on our false alarm probability, and we want to minimize our misdetection probability. So there we are saying, well, X is an element of A0 if, and here we introduce a very important concept, the likelihood function. And actually we've been using that now for a whole time because it's simply defined as the probability of X conditioned on H0. So that actually should be more exact and show the argument of small x, right, our measurement result. This should be in all of these probabilities here. I was just didn't want to spend the time of writing it down, but it's here basically saying that this ratio of those probabilities is our likelihood function of the small x. And we are saying, well, we decide that it's element of A0 if this is larger or equal a threshold gamma, where, and this is now not necessarily the same threshold that I had for the radar problem, right? But gamma is the largest value such that the sum of all x such that the likelihood function being smaller than gamma of the probability of gamma x conditioned of h0 of x is smaller or equal than alpha. So this is a very roundabout way of saying that our misdetection probability, our false alarm probability has a constraint of magnitude alpha on it. And so here we're just saying that, well, we have to find the gamma in a way that the false alarm probability fulfills that constraint on alpha. So this is an implicit equation for gamma. And then it is that gamma that we have to use as a threshold in the actual likelihood test. And of course, for the continuous case, and this is all for discrete variables, for the continuous case, in this and all previous examples, all the p of x condition of h0 of x are replaced by the probability density function. And then the sum here is replaced by its integral. Now this Pearson test is something that you will find very often in detection theory. So let's maybe give a sketch of a proof of how we are getting to this formulation. And we have to define a function that we want to minimize. And we're saying that, well, this is the misdetection probability. Let me actually write this down. Minimize PMD under constraint on PFA. And then I have to bring in the linear constraint. And so I'm doing that with the Lagrangian. Meaning I'm putting here, this is my Lagrange multiplier. Times false alarm probability minus alpha. Right? Because that is my inequality constraint. I want the false alarm probability to be smaller than alpha, or equivalently, I can say I want the false alarm probability minus alpha to be smaller or equal than 0. So that brings it into a standard form for which we know that this is sort of the proper Lagrangian formulation. Right, so if we're now dealing with a continuum, then we're saying that, well, this is the integral over our decision region f of x conditioned on h1 x dx. Right, so I'm making a decision for a0 even though h1 is true. And that is the definition of a misdetection, and I'm integrating this, of course, over my whole set A0, meaning any outcome that lies in that A0 partition is a misdetection. So that's just standard reformulation of what is PMD. And then I'm saying plus lambda of, and now my false alarm probability, I'm going to rewrite it as 1 minus the integral over A0 of fx conditioned on H0 of x dx. So I'm just saying that, well, my false alarm probability is 1 minus the correct alarm probability dx, and minus alpha. Which I can now rewrite as the integral of A0 of fx conditioned on h1 of x minus lambda of fx conditioned on h0 of x dx plus lambda times 1 minus alpha. Which, by the way, also implies, of course, that lambda has to be larger than 0. So now we can state that for a given lambda and alpha, right, our G is minimized if A0 includes all x, for which fx conditioned on h1 of x minus lambda of x conditioned of h0 of x is smaller or equal than 0. And I have an integral of this function here over a certain area. As long as that function value is negative, it's going to depress my overall integral. If it gives me a positive value, then it's going to increase that integral. Since I want to minimize this function here, I'll want this thing here to count only when it's smaller or equal than 0. And that now means that, well, I want to make sure that my ratio fx of h0 of x divided by fx conditioned on h1 of x has to be larger or equal than 1 over lambda. And that lambda is just what we're now calling that threshold gamma. And now we again just have to say, okay, what is the side constraint under which we are actually fulfilling our false alarm probability? And that's already the equation that I gave before. Okay. I have here a whole set of examples to show you a comparison of these four estimators, but we are seriously falling behind time. So if at the end of the lecture we're still going to have time, I am going to go through the examples. But for now, let's take our break. It's 8:51. We're going to resume at 8:56, and then we're going to start talking about estimation of random variables in linear regression. Okay, let's get restarted. So we are now going to deal with estimation of random variables. And in particular, we're saying, well, what is the problem? Well, we want to estimate or calculate the approximate value of a random variable that has not been observed based on actual observations that we have made. And to make it a little bit more intuitive, if you're saying that a random variable is in the future, then it's basically just a prediction. And you might say, well, I have a time series observation of a random variable and that is fluctuating back and forth, and I want to be able to make a prediction of what is that variable going to be at some time in the future. Right? That sort of estimation or that sort of prediction, again, has a whole bunch of applications. From my particular area, again, and you, for example, measure the channel state information, let's say the strength of the wireless propagation channel, and you want to predict how strong is it going to be 10 milliseconds from now. And the motivation for that is you have to make now a decision of who's going to be allowed to transmit 10 milliseconds from now. You have to decide on which modulation format, which signal strength you're going to use. So you need to basically look into the future and say what is most likely going to be the value of my signal strength or the realization of my random value signal strength that I'm going to have. And another example is the stock trading. And as you know, until about 30, 40 years ago, it was pretty much long-term. People looked at the fundamentals of companies, were saying, okay, this is going to be successful, this is not going to be successful. Then Dr. Simon, who was actually a math professor, came up with interpreting stock prices as random variables and analyzing them and doing the prediction of these random fluctuations. And that sort of quantitative financial trading has now become a multi-billion market. I think he became a centibillionaire just based on that particular principle, and a lot of other companies have taken that on now as well. And there's lots of other applications where you're saying, well, I have my time series observations. I want to find out what is the future value going to be. You can also have just a decision about interpolation, and where you have observations, for example, at particular locations, and you want to find out what might be a random variable realization somewhere between the points where you have measured, and so on. So what are we trying to, or what are the different ways in which we can do our estimation? Well, first of all, we're usually trying to do a minimum mean square error estimation. So this is MMSE. So we are defining our mean square error as the expectation of x minus x hat squared, right, with x hat is the RV to be estimated. And we want to minimize that mean square error. Now, why mean square error and not, for example, the mean absolute error, which is also a valid criterion? And you could say, well, x minus x hat, that would be the mean absolute error. You probably have about 1,000 applications for this one here, for every one application of this one. Well, partly it is because the square error in a lot of situations can be physically linked to other quantities that you are interested in. For example, again, in communication and information theory, there is a relationship between the capacity and the mean square error. But another important reason is that this error, the mean square error, is typically analytically tractable, while the mean absolute error is not. Mean absolute error, or you could also say you're dealing with an L1 norm, is not catastrophic from a computational complexity point of view because it's still convex. And actually, when you're looking at sparse optimization, the L1 norm is often used as a proxy for the L0 norm because it is analytically tractable. But still, you need linear programs in order to solve the optimization, whereas the mean square error is just giving you results in closed form. So this is a strong motivation for going with this particular criterion. So that being said, we're going to be talking always now about the mean square error. And first type of MSE estimation is the blind estimation, which means that only the probability model is known. And then what's our best estimate for a random variable? We write that as x hat, meaning estimate, the subscript b for blind, and it's just the expectation of x. If we don't know anything about any realization, all we know is the probability model, then we're saying that, well, the expectation is the thing that's most likely to come up, or sorry, I shouldn't say that's most likely to come up, that is going to minimize the mean square error, and actually we showed this previously already. And the associated error that we're getting then, the error resulting from the best, which is the start here, blind estimate, is just the variance of x. So that's not terribly insightful. What we are much more interested in is the estimation of x given an event. And so there we're saying that, well, we have x hat given event A, and that is just the expectation of x conditioned on A. And I'll remind you of an example for this estimate that we already did a little while in the past. And we were talking about phone calls and assumed that the duration was exponentially distributed. And then we said, well, what if we've observed that the phone call has already lasted 2 minutes? What is the expected value of how long the phone call is overall going to be? And so the probability model here is that we have a call duration which is exponentially distributed with a 3-minute call duration. And then we say, well, our probability that of a duration t, conditioned that t is larger than 2, of t is 1/3 times e to the power of minus t minus 2 divided by 3 for t larger equal 2 and 0 otherwise. And that means that the expectation of t, condition of t larger 2, right, is just the integral from 2 to infinity over this function here. Right, and that is two plus 3, which is 5 minutes. And just as a reminder, right, this is the memory-less property of the exponential random variable. And so no matter when you start the observation, the rest always looks the same. So if you start to observe only at time t equal to 2, the expected duration of the call is still 3 minutes. If you start to observe at t equals 0, expected duration of the remaining call is 3 minutes. If you start to observe at t equal 100, and then you just look at these very, very long-lasting phone calls, and the expected value of the remaining duration is still 3 minutes. Now, going a little bit further than that, right, this was conditioning on an event. Now we're going to condition it on the realization of another random variable. And so we're saying we're looking at the estimation of x given y. So xm of y is the expected value of x conditioned on y taking on the value small y. And you're going to see that, obviously, there is a requirement that y is in some form correlated to x if we want to find out information, if we want to get any decent amount of information out of knowledge of y. And if y is uncorrelated from x, then this here becomes identical to the blind estimator. So if we now have a whole bunch of, let's just say, we are dealing now with the fundamental model that xl, meaning a linear estimator, xl of y is ay plus b. And that is the fundamental linear regression problem. At the moment, it looks still very simple because we are just dealing with one realization, and we're going to go to the vector case in a little while. So we're now saying that the values AB of an optimum linear estimator depend only on expectation of x, expectation of y, variance of x, variance of y, and the covariance of x and y. And then the error that we're going to get is the expectation, and that is now the unconditional expectation of x minus xl hat of y squared magnitude. Right, so when we're dealing with the linear expectation, with the linear estimator, with this particular model, we're basically saying that only first and second moments of the random variables are playing a role. That also gives you the idea already that this might not necessarily be the optimum estimator overall, and sometimes nonlinear estimators are going to give you better results, and there you would take into account more information higher order moments about your particular random variables x and y. You can probably also already make a guess under what circumstances is the linear estimator the optimum estimator. Gaussian, exactly, because a Gaussian random variable is completely determined by its first and second moments. At the higher order moments, there is no additional information in them. Therefore, we are not losing anything by throwing them away in our estimation. And so the optimum linear MSE estimator of y given x is, x given y is x hat of y is rho xy, sigma x over sigma y, y minus vy, plus vx. So that is the LMSE estimator. And it has two important properties. The first one is, what is the actual MMSE that we're getting? Well, it's an epsilon L star that equals sigma x squared times 1 minus rho xy squared. And the estimation error, x minus xl hat of y, is uncorrelated with y. So let's look at this equation a little bit. first of all, we're seeing that the means don't enter here, right? Which is not exactly surprising. If we have known means for x and y, well, the random fluctuations around them and the error that result from those random fluctuations are not going to be influenced by the mean. And then you can also see here that, well, what is my mean square error? Well, if I had no knowledge of, or if the x and y are uncorrelated, then I see that my mean square error is just a sigma x square, which is exactly what we're getting from a blind estimator. If the error is if there is some correlation, then we are appropriately reducing the mean square error. If I have full one-to-one correspondence between x and y, meaning my rho is 1, then obviously the moment I know y, I also know x, and my MMC would be 0. And so this is fairly intuitive. Now, the other the other statement here is maybe a little bit less intuitive, but still very important, which says that whatever residual error I have from my estimation is uncorrelated with y. And well, I guess, again, the intuitive interpretation of that is to say that I exploited all information in y that is useful for the estimation of x. And so I've squeezed out every bit of information that helps me in improving my estimate of x. Whatever remains is uncorrelated with x, and therefore doesn't give me any, wouldn't help me to further improve my estimate. And again, no matter what type of filter you're using, Wiener filter and so on and so forth, this property is very often going to play a role in your development, in your system analysis. So because this estimator is fairly important, I'm going to run with you briefly through the derivation. So we first of all say, what is the error that we're encountering? Well, we're taking x hat being ay plus b, and we plug that into the equation that epsilon is, of course, the expectation of x minus x hat squared. And I'm dropping now that x hat of y, just for notational convenience. And so that, of course, tells us that this is the expectation of x minus ay minus b squared, and which we can further write as expectation of x squared minus 2a expectation of xy minus 2b expectation of y plus a squared expectation of y squared plus 2ab expectation of y plus b squared. And then I just say, well, let me take the derivative of that with respect to a and b, and because those are the parameters that I want to optimize. And so this is minus the expectation of 2xy plus 2a expectation of y squared plus 2b expectation of y being 0. And that has to be 0 as well. And then from that, I can now get a system of two equations that tells me, well, my optimum A is the covariance of xy divided by the variance of y, which is rho xy sigma x divided by sigma y. And then my B star is the expectation of x minus A star times expectation of y. Right? And what you need to keep in mind here, of course, is that the covariance of x and y is the expectation of xy minus the expectation of x times the expectation of y. And so that's how you're getting to this particular equation here. And so by now using the notation of mu x and mu y for the expectations here and the expressions for the covariance and variance, we can now write our overall error as mu x squared plus sigma x squared minus 2 rho xy sigma x over sigma y rho xy sigma x sigma y plus mu x mu y minus 2 times mu x minus rho xy sigma x over sigma y mu y mu x plus rho xy squared sigma x squared over sigma y squared plus mu y squared plus 2 rho xy y plus x minus rho xy sigma x over sigma y mu y squared. Okay, and I'm not going to write all the different steps. This is pure algebra, and it's not really, I think, interesting for you to look through all the different steps. I ran through it last weekend, and you can see here that this whole thing of things is just most terms are canceling each other out. You will see this on the video later on if you actually want to follow through and look at it. But in the end, you are getting something fairly straightforward, namely sigma x squared minus rho xy squared sigma x squared, which is exactly the equation for the mean square error that we had before. And then if we want to look at or if we want to prove the error orthogonality, again, setting it up is relatively straightforward. We're just saying, well, we want to find the expectation of the product of y with the estimation error, right, which is x minus x hat. We're saying, what is that estimation? Can we please have my finger as part of the camera? I'm pointing to something on the, thank you. we have this equation here that says expectation of y with the residual error. Right? And the residual error is estimation error is x minus x hat. And then we're just doing the same thing. Right? We're plugging in the expression for x hat, which becomes this thing here, because now we already know what is our optimum A and B. And then we replace the expectation of x and y with the with covariance plus the mean, and all of the other terms. We check this all out, what can be cancelled out, and lo and behold, it all adds up to be 0. Right? So the only things you need to remember about these proofs is the principle. Well, we're taking as our starting point this equation here and plug the solution for x hat in. The rest is just algebra. So, a couple of comments to this solution. First of all, the intuition. I already mentioned it, but I want to write it down because it's important. The more correlated the random variables are, the better we can estimate one from the other. Now, we can also run into the situation that y is deterministic. So there is, for example, the situation that in wireless communications, again, the path loss that you're encountering, which is sort of the inverse of what is called the channel gain, and in other words, path loss is attenuation. And the law is that this path loss, as a function of distance, is some constant multiplied with d to the power of minus n. That's at least on average, plus some random variable, s, which is called the shadowing variable, which is known to be log normal. And this is d is the distance, is deterministic. Now you look at this problem and you're saying, what does this have to do with linear regression? And everything here looks completely different. Well, multiplied. Now, what we can do here, first of all, is we're taking the logarithm of this whole thing. Then we're getting our path loss in dB becomes a value alpha plus value beta times the logarithm of d over d0 plus a variable that we're calling now s prime, which is Gaussian. Now you're just reinterpreting this logarithm of d as some value of d prime, and it's just basically a different axis on which you're plotting. And now you're saying that, well, what is actually the problem? I'm doing measurements. I'm plotting here logarithm of d over d0. I'm plotting here my path loss in dB. And, well, I'm going to get something that is a linear regression. This is a linear function. This is an alpha plus beta times d prime. And the actual values are going to be distributed somewhere like this, and with random variations around this fit here, and with a Gaussian distribution. And so I have these points here as measurements, and I want to find out what is the best line that I can fit in here, such that the mean square error, meaning the deviations that I'm seeing here, is going to be minimized. And then my best estimate, meaning my prediction is, well, if I'm picking some random value here at a different distance, saying that, well, that's my best estimate for what the path loss is going to be at that location. And so this is an example of how a problem that seemingly has very little to do with linear regression has to be somewhat reformulated, a little bit massaged, in order to fit into this framework of what I want to do here. And once I understand that this is the problem that I need to solve, then you can take your measurement values. It's very easy to find out what is the best linear fit here. Right? But first of all, you have to realize that, okay, this, which looks nothing like a linear regression, can be reformulated as a linear regression problem. That is very often the first and most difficult step that you are encountering. Then, again, repeating what we already said, that for bivariate Gaussian variables, LMSE is optimum. But in general, LMSE is worse than an MMSE, since it uses less information. Now, another very interesting fallacy is, or thing you have to watch out for, is the following. The best prediction is more average than the observation, but that does not mean that the population statistics change with time. So what do I mean by that? Right? Imagine that. Actually, let me give you the example that that gave rise to that fallacy and the counteracting. And in the military, for a long time, IQ tests were applied to all recruits. And then you can try and make a prediction and saying that, well, from one generation to the next, can we predict what is the IQ going to be for the next generation of the recruits? Now, whenever you're making such a prediction, it will always be more centered towards the average. And because if just imagine the extreme case, you know nothing about correlations, you don't know anything, your best prediction is just going to be the expected value of the distribution. So if you know nothing else, you just say, okay, I have a distribution with IQ tests, let's say with a standard deviation, with a mean of 100 and a standard deviation of 10, so my best prediction for the next generation is going to be the IQ is 100, purely. And which would mean that everybody is more average. There is less people with much higher, less people with much lower IQs. And so that would give the impression that, well, as time goes by, you have a complete averaging out of the IQ. Now, you can see very easily that this is a fallacy. Because if you just revert time and say, let me take the current generation and predict from that what the IQ distribution of the previous generation was, then you would say, hey, actually, it's the previous generation that had the more evened out IQ distribution. And both of these things cannot be true at the same time. And so that was the problem that arose in the social sciences community, where there was a long debate about that. You can draw very similar conclusions in electrical engineering. Again, just try to do the prediction for the path loss. And then you're saying, I'm going in this direction. I have my distribution, attenuation due to fading. And I have my variations around the mean path loss, and my prediction is always going to be more and more centered on the mean path loss value, because it's very hard to actually predict the statistical variations around it. So you would think that the fading distribution becomes narrower and narrower as you go further and further that direction. But now, when you are walking back, you're of course experiencing the same fading dips, same fading peaks, everything the same that you had when you were walking in that direction, and because you're just in the same location again. And so similarly, you have to say that, well, my distribution of the fading is not going to change. It's not going to depend on do I go in this direction, do I go in that direction. And so again, it's a thing about what is my best estimate, what should I be using in order to minimize my prediction error. It's not saying that my actual statistical distribution, my fading distribution and so on, is changing or is becoming more concentrated. So up to now, we've been talking about having one random variable, one x and one y. Now we're going to a slight generalization. We're saying linear estimation of random variables from random vectors. Actually, the path loss model that I showed you before already went into that direction. So we're saying x, just for simplicity, we're saying x is a random variable with an expectation of 0. And y is an n-dimensional random vector with expectation of y also being 0. Then we're saying our best estimate of x given our random vector y is the correlation vector xy multiplied with the inverse of the correlation matrix of y times y, where we're defining the correlation matrix as the expectation of y transpose, and the correlation vector between x and y is the expectation of x times y transpose. The MMSE that we're getting in this case is epsilon star L. It's the variance of x minus r xy r y to the power of minus 1 times r xy transpose. And again, the estimation error is uncorrelated with the elements of y. And so the important thing that you see here is that, first of all, the autocorrelation properties of your vector y are coming into play. And on the other hand, the cross-correlation properties between x, between the thing that you want to estimate and the thing that you want to observe, is coming into play as well. And so this is, again, not terribly surprising. And it's just a generalization of the case that we had for when y consists of a single variable. And as a matter of fact, if you just reduce the dimension of your vector y to a single value, then so if you're just saying dimension of y is 1, then you're of course just coming back to the equation that we were previously discussing. And because the autocorrelation function of y just gives you the sigma y square, and so you divide by sigma y square, you multiply this with the cross-correlation vector, which gives you a rho xy times sigma x sigma y divided by sigma y square, so you get rho square times sigma x divided by sigma y. So, but to give you a little bit of an outline of the overall proof, I'm not going to go through all of the algebra steps now. I mean, it was ugly enough with the scalar. We're not going to do this with matrix. Is first of all, we write the mean square error as expectation of x minus a0 y0 minus a1 y1 minus a n minus 1 y n minus 1 squared. Then we take the partial derivative with respect to the ai. Right, so our epsilon L becomes this is 2 minus 2 times the expectation of yi times x minus a0 yo minus a1 y1 minus and so on. And then we set the partial derivatives to 0 for all I. So now we're getting a0 times expectation of yi yo plus a1 expectation of yi y1 and so on becomes the expectation of yix. And so we're pulling this part out onto the right side. And that can now be written as a0. Then we introduce the correlation coefficient, our r, as an abbreviation for the expectation of yi y0. Note that this r is different from the rho, because rho is between -1 and 1. R is just the expectation of yi y0. So this is now our system of equations that we're dealing with, and that can just now be written as, well, this is just our correlation matrix of the y times our vector a, and on the right hand side we have now our vector r, y, x. And that can be rewritten as our vector a should of course be r, y to the power of -1 times r, y, x, or since x is a transpose y as our best estimator, that leads us now to the final equation. Right? Remember a transpose, so that means we have to take r, y, x transpose as the first term, and r, y, x transpose is r, x, y, multiplied with r to the power of -1. Transpose of the autocorrelation function is the autocorrelation function itself, right? And that multiplied with y, which was what we wanted to prove. And if you're an enthusiast, then you can prove the second part, namely that the residual error is orthogonal to the y yourself. And if we have a non-zero mean, then the whole thing just becomes formally a little bit more difficult, but it's nothing significant changing. And first of all, we're dealing now with the covariance matrices or vectors instead of the correlation vectors. So we're dealing here with c, xy, cy to the power of -1 applied to y minus its mean. So we're subtracting the mean from our vector y, apply the correlation to it, do all these computations, and then at the end we add on the mean for our vector is a scalar x. Thank you. And the residual error is the variance of x minus, and here we have again autocovariance function. The mean obviously doesn't enter into this particular equation here. And if x is an n-dimensional vector, then we have pretty much the same equation. Now it's just everything is matrices because we have correlation matrices and cross-correlation matrices all over the place. Okay, that wraps it up for today. Thank you very much, everybody. Reminder, next Tuesday, no lecture at Veterans Day.